Hi, my name is Christopher Jones, and in the next few minutes I want to give you a very brief introduction into Modelica and Dymola. To start things off, I want to clarify some terminology. So, what is Modelica? Modelica is a non-proprietary modeling language to model multi-physical systems, and Dymola is a development environment with which you can easily build Modelica models, compile, run, and simulate them. With that, I want to start with the key advantage that Modelica brings to the table, the fact that you can model multi-physical systems. And what do I mean by multi-physical systems? Well, in any given complex system or even in simple systems, you will typically want to model and simulate multiple physical domains together within one simulation model. So in the example of an electric vehicle, you might have vehicle dynamics behavior you want to simulate, you have electrical behavior, you have mechanical behavior, you might even have fluid and thermal behavior that you're looking at. And while there are lots of tools out there that can model and simulate individual domains very well, where Modelica really excels is modeling all of these domains together in one model and gaining insight about the overall system behavior. With that, what could this look like if we look at a very simple multi-physical model? Here we see in the middle we have an electric machine which is powered by a constant voltage. So we have an electrical system. There's a mechanical shaft on the electric machine which models rotational mechanics, and we have a load applied to that. We can also add a very simple thermal model to our electric machine which we could then easily cool by adding a liquid cooling system. Now we can look at the simulation results of this complete multi-physical system. We can run it and then plot simulation results. For example, we can look at the core temperature of the electric machine, or we can look at the applied and resulting torque on the machine shaft. So that's what we talk about when we mean multi-physical modeling. Now, in order to actually explain the value of Modelica as a modeling language, let's look at an example. Let's consider a simple suspension system that you might find in any given system, just containing a mass, a spring, and a damper. In the center, you see how you would sketch this out on a piece of paper, and on the right-hand side, you can see the equations that govern the system behavior. Now, there are two fundamental ways of modeling such a system. The conventional way would be to use signal flow based diagram, in which we take our physical equations, we Laplace transform them, and then we can map out the system behavior by looking at signal flow between different components. This has been done for many years and works. Let's contrast that with the model that we build in Dymola, which is built in a very engineering-friendly fashion. We can identify all the individual components just like we see them within the sketch that we saw previously. Now, within Dymola, we can then model both types of systems and run them. And we can then simulate the model and compare the simulation results. And then we'll see that the system behavior is clearly the same. Both models are representing the same underlying physical behavior. So both of these methods yield the same results. However, things get more complicated if we add more components to our systems model. So let's assume we want to extend our systems model that we saw earlier, the spring mass damper system, and we might consider just adding a second spring mass damper system. Again, we can model both of these in different fashions, either the signal flow-based diagram, where we can already see it gets increasingly complicated and it's not at all apparent what the individual components of this system mean and how they're connected. Again, let's contrast that with the component model that we build in Dymola. Very engineering friendly. It's immediately apparent what this system is supposed to represent and how it works. Again, both these systems can be simulated and they will yield basically the same results. What we're actually plotting here is the position of the masses of our system while we're applying a force. And you can easily imagine things get very complicated very quickly if you build a complex system, or even within this system. Let's assume you want to remove a spring component. In the Dymola model, nothing simpler. We mark it, delete it, and it's gone, and we can run simulations using this. However, if we go into the signal flow-based diagram, it's not at all apparent if we can just remove the spring gain component. We can't begin to hope that removing a single component from this system will make it behave in any way, shape or form the way we are expecting it to. Basically, we would have to go back to the drawing board, write down all the equations, transform the equations into assignments in order to then model out the system. So it's a very tedious, manual and time-consuming process. Another example to highlight the difference between the causal modeling using assignments and the acausal modeling using equations in Modelica can be seen by just looking at a very simple resistance model. Basically, a resistance model typically has three quantities associated with it: the resistance R, the current I, and the voltage V. And depending on which of these quantities we want to determine, we would need three distinct models when modeling this in a signal flow-based diagram. If we want to calculate the resistance, we would need a model that takes the voltage and the current as input to calculate the resistance. Or if we want the current, we would need a different model taking the voltage and the resistance as input and the current as output. However, the Modelica model of a resistor literally contains the physical equation the way we find it in any physics textbook. Here we see the equation for the resistance, which takes all three quantities into account, and depending on how we're exciting our model, the equation system will solve itself to give us the desired output. So we've already mentioned the fact that Modelica is component-based. Now, what does this actually mean? Just like with building blocks, we can use these individual building blocks in a multitude of different models. We're not limiting ourselves to use individual components only within a certain scope. So let's look at the example we already saw previously, our simple electric machine. We see a lot of components in here that are very generic and can be used in lots of different simulation models. This also talks to the overall object-oriented nature of Modelica, where we can use all the concepts from object-oriented programming and modeling that we've come to know and love, such as inheritance, encapsulation, abstraction, and many more. Now that we've introduced components, the next logical step would be to group all these components. And Dymola comes out of the box with the Modelica standard library, which is developed and maintained by the Modelica Association, who are also the guardians of the Modelica language standard definition. The Modelica standard library itself contains all the base components for many different physical domains that you might need. So if you need a resistor model, there's no need to define your own resistor model. The Modelica standard library comes with a simple resistor model that you can just use. Or if you need a capacitor, that's there too. And the Modelica standard library contains components for a multitude of different physical domains, such as electric, magnetic, mechanics, fluid, etc. And just like you could take a very basic toolbox with just a hammer and a screwdriver and potentially build a house, this would probably take an awful lot of time and effort and not be particularly efficient. In the same way, you can take all the components from the Modelica standard library to build very complex systems models that are tailored to your individual needs and use cases. However, if you have a specialized application, such as you want to do woodworking on the house you're building, it might make sense to have a very specialized toolbox tailored to those needs. The same concept applies to Modelica, where you have a whole host of libraries available for different applications and use cases that come prepackaged with specialized components, models and examples for a specific domain. Now, there are some libraries which are commercial, developed by third-party partners of ours. There are libraries that we develop in-house and sell to our customers. And there's also a large variety of open source libraries developed by different research institutes, universities, and just results of PhD theses around the world. So with that, I hope this very brief introduction gave you a better understanding of the value that is inherent in using Modelica for multi-physical systems modeling. And if you have any questions or would like a more detailed introduction or discussion, don't hesitate to reach out to me directly. Thank you very much.